So let's work through some examples in section 2.1, and we're also gonna define some terms like a general solution of an ODE and an initial value problem. So let's start by an example. Solve the ODE. Solve the ODE y prime equals 1 minus y cosine of t. All right. So the first thing we need to do before we start solving our ODE is to put it into the form that we talked about last time. So last time we talked about this form. Y prime plus p of t times y equals g of t. You see that here we have like a 1 in front of the y prime. We have a function multiplied by y, and we have another function in terms of t on the right hand side. So if we multiply this out, we're going to have y prime is equal to cosine of t minus cosine of t times y. And let's add cosine of t to both sides. So we're going to have y prime plus cosine of t times y equals cosine of t. And so our p of t here is cosine of t, and our g of t here is also cosine of t. So let's find the integrating factor first of all. Integrating factor is e to the power of the integral of cosine of t dt. And if we integrate cosine of t, we're going to get e to the sine of t. And we don't need to worry about the constants. Like I said, you don't need to worry about the constants. So we're going to have the integrating factor is going to be e sine of t. We multiply this to our differential equation. We're going to have y prime times e to the sine of t plus e to the sine of t times cosine of t times y equals e to the sine of t times cosine of t. Like I said before, doesn't this seem familiar to you? When we look at this expression right here on the left-hand side, like, can't we notice that this represents something? So we have a derivative. So let's say we have y and e sine of t. If we think about it, if we take the derivative of y, we're going to have y prime. So we're going to keep e to the sine of t. And if we take the derivative of e to the sine of t, well, the derivative of sine is cosine of t. So we're going to have cosine of t times our function, times our exponential function, times y, keeping our first function. And this is going to stay the same. So this, you're going to get better with practice, but this is equal to the derivative. I'm going to write it right here so it becomes clear. So this right here, you can rewrite it as the derivative with respect to t of y times e to the sine of t. And that is going to be equal to e to the sine of t times cosine of t. All right? And since we want to solve for y, what do we do now? Well, we integrate both sides. So we take the integral with respect to t, take the integral with respect to t. And since integration and differentiation undo each other, all we're left is our argument. So y e to the sine of t is going to be equal to this integral right here. Right? And how do we solve this integral on the right hand side? I think it's pretty easy. Well, let's use u substitution. Let's call u sine of t, and if we differentiate it, du is going to be cosine of t dt. And I usually solve for dt, so dt is equal to du over cosine of t. And we can rewrite this integral as the integral of e to the u times cosine of t times du over cosine of t. And the cosines are going to cancel out. All we're going to be left with is e to the u. So we're going to have y e to the sine of t is going to be equal to e to the u plus c, right? But we can't leave it like this because we were the ones that defined u, so we have to plug it back in. So u was sine of t, so y e to the sine of t is equal to e to the sine of t plus a constant. This right here is what it's called an implicit solution to our differential equation. You see that y is not given explicitly. It's y times something else. This is a solution of the differential equations. You can leave your answer like this unless it's specified otherwise. But if you want an explicit solution, well, it's very simple. You just multiply everything by e to the power of sine of t. So you're going to be left with, so this is an implicit, I'm going to write it right here, this is an implicit, and an explicit solution would be y is equal to 1 plus c over sine, wait, 1 moment, e to the sine of t. That is an explicit. That is an explicit solution. This is an implicit solution. So this was our first example of how to solve linear ODEs. Notice that when we solve this ODE, we have this constant right here. We have our constant integration. So this is what it's called, a general solution of a differential equation. And let me define it for you. So the general solution of an ODE involves arbitrary constants. If we want to find c, so to find our constants, so to find c, we need more information. So we need more information, which is an initial condition. So to find the value of these constants, we need initial conditions. And another definition is that an ODE along with initial conditions is called an initial valued problem. and the number of initial conditions also needs to be equal to the number of the order of the ODE. So number of initial conditions, I'm going to call this ICs, so it's going to be equal to the number of the order of the ODE. So, for example, if you have a second order ODE, you need 2 initial conditions. If you have a first order ODE, you need 1 initial condition. So this is relatively straightforward. Let's do one example of an initial valued problem, and I think it's gonna. Solve the IBP. Ty prime plus 2y equals sine of t, where y of pi over 2 is equal to 1 and t is greater than 0. Alright, so let's solve this initial value problem. The first thing we do is that we need to put this ODE into its proper form. So let's multiply everything by t, because remember that the proper form of the ODE is y prime plus p of t times y equals g of t. So we need this to be 1. So we're going to divide everything by t. We're going to have y prime plus 2 over t times y equals sine of t over t. Alright? What is our integrating factor mu? Mu is e to the power of the integral of this expression p of t right here. So 2 over t dt. And if we integrate this, we're going to have e to the 2 times ln of t. And before we simplify even further, using rules of exponents and logarithms, you know that if you have something multiplied by the logarithm, you could rewrite it as a power of the logarithm. So you can rewrite this as e to the ln of t squared, right? And also using properties of exponents and logarithms undo each other. So if you have e to the power of ln, you're just going to be left with the argument, which is t squared. So this is our integrating factor. Next step that we need to do is multiply this equation here by our integrating factor. So we're going to have t squared y prime plus 2t times t squared is just 2t y equals sine of t over t times t squared is just t times sine of t. All right, and this expression here, you might be getting a little bit more comfortable with this. This is just the derivative. We can rewrite this as the derivative of t squared times y. Because if we keep this t squared, we differentiate y. If we differentiate this t squared, we're going to have 2t, and we keep the y. And then our right-hand side is just going to be the same, t sine of t. Now, we're looking for the solution of the ODE, so what we need to do right now is that we need to integrate both sides with respect to t. And by doing that, we're going to have t squared y equals the integral t sine of t dt. And how do we do this integral right here? Well, we do it by integrating it by parts. So if we call u t, so du is going to be equal to 1 dt, and we're going to call sine of t dt dv. It's going to be sine of t dt. So then if you integrate this, we're going to have the integrate of sine is negative cosine of t. And by integration by parts, recall that if the integral of u dv is equal to u times v minus the integral of v du. Basically, if you're multiplying a function, two functions, a function and the derivative of the other function, and you're integrating this, you could rewrite this as the product of the two functions minus the integral of this function times the derivative of this function. So integrating by parts, we have that t squared times y is equal to u times v, so negative t cosine of t, minus the integral of v times du, so negative cosine of t times dt. And simplifying this a little bit more, we know that the integral of cosine of t is just going to be sine of t, and these negative signs are going to cancel themselves out. So we're going to have t squared y equals negative t cosine of t. This is just going to become a positive, because if you pull out this negative, it's going to become positive. And when you integrate cosine of x, it's just going to be sine of x. So we're going to have sine of t, right? But we're not done now, and we have a constant as well. No, we're not done now. This is where our initial condition enters. This is the general solution of our ODE. So this is the general solution. But the problem asks us to solve the initial value problem. So we need to use this initial condition to find the value of c and express this differential equation in terms of c. So if we use that y of pi over 2 is equal to 1, we say that pi over 2 squared times 1 is equal to negative pi over 2 times the cosine of pi over 2 plus the sine of pi over 2 plus c. We just plug this in. Cosine of pi over 2, this is going to be equal to 0 using like our trigonometric circle, and sine of pi over 2 is going to be equal to 1. So we have that c equals pi squared over 4 minus 1. This is our value of c. You can even simplify it even further, like pi squared minus 4 over 4, but you don't need to do that. So our final solution, I'm going to erase this part right here to write our final solution. So our final solution would be, hence the solution of the initial value problem is y of t is equal to, well, let's just write the implicit. Let's write it implicitly so we don't have to like solve for y. So the implicit solution of the IVP is t squared y equals negative t cosine of t plus sine of t plus pi squared over 4 minus 1. So this is the implicit solution of the IVP. If we want the explicit solution, then we just divide by t squared. So the explicit solution of the IVP is y is equal to negative cosine of t over t, because you see that it's going to be t over t squared, so we're just going to be left with 1t in the bottom, plus cosine of plus sine of t over t squared, and then we're going to have our pi squared over 4 minus 1 over t squared. So this is the explicit solution of the IVP. So this is it. This is how you solve an initial value problem for a first order linear ODE. We have the implicit solution here and the explicit solution here. Thank you very much for watching, and I'll see you next time.